Good morning. In this class, I'll cover all the important aspects about a very versatile and an extremely important technique uh, in materials physics. That is Raman spectroscopy. When you're dealing with materials, either in solid form or liquid form, Raman spectroscopy today is indispensable, especially when you're dealing with um, carbon-based materials, graphite, diamond, the carbon nanotube, Buckminster fullerenes, the buckyballs, or the uh, two-dimensional material that is graphene. It's a non-invasive technique. You don't have to give physical contacts like that you need to do in the case of electrical property measurement. And its versatility today is uh, beyond imagination. If you look at the history from 1900 to 1910, uh, reports on the scattering of light have happened. And the prediction of Raman effect came in 1920, and the discovery was announced in the end of 20s. And the same time, uh, Compton effect discovery was announced, and then the notions on the use of Raman effect for chemical analysis were announced. And the double monochromator Raman grading spectrometer was invented, and the resonance Raman spectrometer came into being. And the first use of lasers, laser-based Raman spectroscopy, uh, evolved in 1960s. And then you had stimulated Raman archives, hyper Raman spectra were recorded. And then came the invention of the charge-coupled device. Uh, In 70s, we had the basic principles of Raman spectroscopy in place. Surface enhanced Raman scattering was announced. And then in 80s and 90s, we had a much advanced way of using Raman spectroscopy in the form of Fourier transform Raman spectroscopy with near-infrared excitation. And then the first use of CCD, the charge-coupled device detectors, which are so powerful, were announced for Raman spectroscopy. So it's a great technique. It's a simple technique. It is completely indispensable, as I mentioned, in today's world of material research. The technique, as you can see, it's simple. You need to have an excitation source, and uh, when the source uh, is impinging on material or a molecule, what you see is two processes: the Stokes shift and the anti-Stokes shift. As you can see, in one case, you have reduction in the energy of the incident photons. In the anti-Stokes case, you have an enhancement in the energy of the incident photons. And that's the reason why Raman spectroscopy, Raman process, or Raman scattering is an inelastic scattering process. Whereas the Rayleigh scattering is an elastic scattering process where you see the collision between the photon and molecule results in no change in energy. So you can easily identify this from the color convention given here. H nu remains as H nu, and here there's a decrease in energy, and there's an increase in energy, right? So H nu minus delta E, H nu plus delta E, there's no delta E. It's as simple as that. So what are the basics of Raman spectroscopy or Raman scattering? Starting with the equation of motion, you have this equation of motion m1 m2 by m1 plus m2 times t square x1 by dt square plus t square x2 by dt square is equal to minus k times x1 plus x2. Um, mu times t square q by dt square is equal to minus qx. That's the displacement, and this is the reduced mass. So if you're looking at a diatomic molecule where you have two masses connected by uh, a spring constant k, you can imagine the displacement happening in that form, elongation and compression. And that sort of uh, gives this idea of reduced mass. The solutions are given there always. We have the solutions for the equation of motion q is equal to q naught cos omega t. The normal mode frequency is omega is equal to root of k by mu. Now, the phonon is very sensitive to any change in the spring constant, obviously. So these two atoms are vibrating from their main positions. You can imagine as though the spring attaching to the two atoms, its spring constant changes, and so the phonon that is evolved in that process is very sensitive to any change in the spring constant and the reduced mass. And then any internal and external perturbations can affect K and mu directly or indirectly. And what are these effects? Stoichiometry, doping, strain, pressure, charge, spin. All this can affect these parameters. That's the reason why the changes happening with those small perturbations can be detected in the form of changes in K and mu. Now, if you look at the molecular vibrations concepts, you have a simple harmonic oscillator with omega given as root of K by mu. This is what I mentioned. K is the effective spring constant in the harmonic approximation. We use the reduced field. In the case of quantum, we have a quantum. If you have to give a quantum analogy to this, and, know that the energy levels are quantized, and your E nu is n plus half times reduced Planck constant times root of K by mu. And so the allowed transitions here are delta n is equal to +1 or -1. And this is a typical energy versus interatomic distance concept that we have seen earlier in the earlier classes. Now, if you look at the molecular rotation aspects, we have the classical concept. You have the rotational inertia of the molecules given as I is equal to mu naught R naught square. The kinetic energy of rotation is equal to L squared by 2I. And the quantum analogy is the allowed energy states are E rotational energy is equal to H cross squared by 2I J into J plus 1. So the allowed transitions are delta J is equal to +1 or -1. So what are involved in vibrational modes are always much smaller energies, as I mentioned earlier, compared to electronic transition. Now, this sort of summarizes what I mentioned in the previous slide. These are the rotational modes, the vibrational modes, the electronic transitions that require higher energies to excite and de-excite electrons from the ground state to excited state. But the vibrational and rotational energy spectra, that's the reason why we use high wavelength sources, low energy sources like these energies fall in the range of infrared spectroscopy. So your E nu is equal to n plus half h cross square times root of k by mu, and ER is h cross square by 2i j into j plus 1. Just to give you an impression about this, the strength of the bonds, stronger the bond, you have higher the vibrational frequency, higher the mass of atoms, you have the lower the vibrational frequency. And you look at the carbon single bond, double bond, and triple bonds. For the triple bond, the vibrational energies are higher. These are all in centimeter inverse. And this we know why these changes are happening when we move from the single bond to double to triple bonds. These are various examples that show how the vibrational frequencies are for these different types of molecular bonds. Now, if you look at the electromagnetic spectrum, this is where we talk about the vibrational spectroscopy is recorded in the near infrared to mid infrared regions, whereas the electronic transitions happen at a much higher energy. That's where you need UV and visible radiation as the excitation source. That's the main difference between, electronic spectroscopy and vibrational spectroscopy. If you look at the classical theory of Raman scattering, you have the oscillating electromagnetic field that induces a dipole moment. I explained about the concept of dipole moment in the previous class. If you have a charge separation, you have a positive ion separating from the negative one, or in the case of an atom, if the electronic cloud is displaced with respect to the positively charged nucleus, and that displacement would give rise to an effective polarization, because you're getting an induced dipole moment. Polarization is equal to alpha E, that alpha is the polarizability, E is equal to E naught cos 2 pi nu naught T, and this P is induced dipole moment. So this P is equal to alpha E naught cos 2 pi nu naught T. The polarizability varies with the direction of the electric field. You know this. The Taylor series expansion of polarizability coordinate about the equilibrium position is given by this relation, alpha is equal to alpha naught, dou alpha by dou r minus r. Now the vibrational displacement Q of the ith mode is given by this equation, Qi is equal to Q naught cos 2 pi nu it, and the equation for the polarization is that what we see is this component is the Rayleigh scattering, and that corresponds to this Stokes shift, and that corresponds to the anti-Stokes part of the process. Now, the condition for a mode to be Raman active is simply that your dou alpha by dou Qi should not be equal to 0. Okay, that's a condition, and the intensity of the Raman scattering depends on the polarizability, as this goes as I scattering is equal to dou alpha by dou Qi whole square times I naught square. Okay. Now, we have seen this also in the earlier classes. All these molecular vibrations, the stretching modes, the wagging, twisting, rocking, um, scissoring motion, and the symmetric, anti-symmetric stretching, right? All this involves uh, energy which falls in the infrared range. And what we are doing using the spectroscopy techniques is we're capturing all the information about the vibrations of molecules. Now, a linear molecule with n number of atoms has 3n minus 5 normal modes. A nonlinear molecule with n atoms has 3n minus 6 normal modes. Now, the stretching modes have higher energies than bending modes. This stretching modes have higher energies than bending modes. For example, in C6H6, we have 12 atoms and it is nonlinear. Right? So there are 3 into 12 minus 6, 30 normal modes in this particular molecule. Now, what are the selection rules? Infrared spectroscopy and Raman spectroscopy are both used to measure the vibrational energy levels of molecules and crystals, and in one way, they're also complementary. In order to get a complete information about the kind of modes that are present, sometimes you need to do both spectroscopy techniques. We need to use both the spectroscopy. If you look at the IR active modes, vibrational modes are IR infrared active. If the dipole moment of the molecule changes during the vibration, for example, the symmetric stretching in carbon dioxide is not IR active. It's not this. But the asymmetric stretch mode is IR active. Now, the Raman active mode, for a transition to be Raman active, there must be a change in the polarizability of the molecule. There must be a change in the polarizability of the molecule. And the polarizability tensor determines the moment induced by an external electric field. That is, Raman activity can also be expressed as d alpha by dq, q is equal to 0 is not equal to 0, where q is the normal mode coordinate for the vibration. If a molecule has a center of symmetry, modes which are infrared active will be Raman silent, and vice versa. Now, Raman, what are the Raman selection rules? Only modes which have a change in polarizability are Raman active. Always remember this. This is one of the basic principles of how Raman modes can appear. Only modes which have a change in polarizability are Raman active. For rotational transitions, we consider Raman scattering a two-photon process. That is the incident and emitted, when the incident and emitted photon are photonic energies are evaluated. Since each photon transition has delta J is equal to +1 or -1, the scattering satisfies delta J is equal to 0. That is the Rayleigh scattering. There is no change in energy. It's an elastic scattering process, Rayleigh scattering. Whereas Raman scattering is an inelastic scattering process. Now, the delta J is equal to +2, the Stokes transition. Delta J is equal to -2 is the anti-Stokes transition. For vibrational transitions, the change in vibrational quantum number for the overall transition must be delta N is equal to +R -1. Well, phonons play a very important role in materials physics. A perfect crystal is a spectrum of lattice vibrations. Lattice vibrations are phonons. These are periodic vibrations, quantum vibrations of atoms in the crystal with a well-defined wavelength. The first Brillouin zone is the Wigner side's primitive cell and reciprocal space. Only wave vectors in the first Brillouin zone are physically significant for phonons, right? Wave vectors in the first Brillouin zone. And the first Brillouin zone is called the Wigner side's primitive cell. This is because any other wave vector can be translated to a wave vector from the first Brillouin zone, that is the Wigner side cell can be used for translation. There are two types of phonons in solids, the acoustic and optical phonons, phonon optical modes. With n number of atoms in the basis, in three-dimensional lattice, there are 3n normal modes. 3 modes are acoustic, frequencies vanish linearly with k in the long wavelength limit, and 3n minus 3 modes are optical. So just to give you a quick idea about, if you have a two-dimensional lattice, two-dimensional lattices can be represented in all these forms. So possible choices of primitive cells for a 2D driver lattice, and that is your Wigner sides lattice, where you can account for one atom per unit cell, and this is the smallest unit that can be used for the vectorial translation. I also mentioned about the basis, but just to give you a little more idea pictorially, what I've shown is this is a space lattice. This is also a space lattice. This space lattice has one atom at each of those lattice sides. This also has one atom, but this one atom has has an additional atom attached to it. So this whole entity has to be considered as basis, because it's the same repetition of this unit in the space lattice. So the basis here is one atom. Here also that unit is a basis, right? So the basis has to be defined like that. And we know that once you have the basis defined, you have the primitive cell identified, you can easily do the fundamental translation using the simple vector mechanics. That's a two-dimensional lattice, the oblique arrangement of atoms showing the primitive lattice, and that's a simple cube, which itself is a primitive lattice. Right? Yeah. The oblique lattices can be represented in all these ways. Several possibilities in which pairs of 2D primitive vectors can be identified to represent the driver lattices. And that representation shows the concept of Brillouin zones. You have Kx, Ky, and the first Brillouin zone is missing there. Is equal. It's the scale here is minus 5/8 to plus 5/8, minus 5/8, and plus 5/8, minus 5/8 here, right? The denominator is missing there. Please note that. Now, if you look at the phonons, lattice vibrations or phonons are not random in 3D materials. If n is the number of atoms per unit cell, then you have 3n total number of lattice vibrations. Right? This is a typical well-known representation that you will see in all solid-state physics textbooks when you plot omega k versus k, that is wave vector. So 3n total number of lattice vibrations. 3 and -3 is optical phonon modes, and 3 acoustic phonon modes. Some are Raman active, and some are infrared active. All right. Yeah, that shows the representation of acoustic phonons and optical phonons. Yeah. Now, talking about the intensity of Raman scattering, the intensity is proportional to omega to the power 4, which is a dipole radiation transition. And this term comes from the Raman selection rules, and this term comes from the resonance effects. Where here, R is a Raman tensor. EI and ES are the incident and scattered polarization vectors. E alpha and E beta are the intermediate electronic states of the crystal. And the Raman active modes can be determined by symmetry considerations from the crystal lattice. So what are the advantages of this versatile spectroscopy technique? The advantages are light does not have to pass through the sample. You can do the experiments in the reflection mode. You have a sample, you have the light impinging on it. If you have a detector on the source side, you can get all the information from the reflection mode itself. You can use a wide variety of materials using this process. Wide variety of materials can be analyzed, and all the processes related to the vibrational spectroscopy can be easily understood. There's no sample preparation required here. It's a very straightforward. You take the sample, put it in the spectrometer, and you start doing the measurements. Spectra from each material are unique. I also mentioned this, that you get signature fingerprint patterns of each material. So like the fingerprint patterns available for when X-ray diffraction is done. In a similar way, you have all the recorded fingerprinted patterns of the materials available in the handbooks and in the archives, and you just have to compare it and see whether the Raman spectrum recorded on the material that you have prepared is matching with the fingerprint of the material or not. It's a completely non-destructive process. The sample is not destroyed, and the analysis also happens quite quickly, quite fast. Now, what are the applications? Various applications there. So of course, it's a non-destructive technique, and you can measure the shifts in phonon frequencies, measure the local environments, changes in the way the bonding is affected by doping and pressure and temperature. All that can be recorded, and strain that is induced in the lattice, external or internal strain. Internal strain comes because of doping. External strain is the hydrostatic pressure, and both this process can cause strain in the material. And when a material is strained, you have you suddenly see changes in the bond angles and bond distances, and all that information can be easily captured using this very simple and versatile technique. You can also study phase transitions in crystals, and fingerprinting of molecules and materials I've already mentioned about. Now, every technique has its own advantages and limitations. And what are the limitations of Raman spectroscopy? I also mentioned that of all the spectroscopy techniques, the scattering cross sections in Raman spectroscopy very small. So that's the reason why the effect is very weak. But of course, today we have very powerful detectors in the form of CCDs that can capture information from uh, extremely small intensities that evolve during the Raman scattering process. Otherwise, the points to be noted are weak effect. It's one of the limiting factors, whereas the Rayleigh scattering is about 10 to the power of 5 times more than that of Raman scattering process. Samples with color may absorb laser light, and they can also. One of the problems is in laser Raman spectroscopy, the uh, uh, emitted light intensity is very powerful. It can be very strong because we are using a laser as a source, but you can have laser-induced damage. That's one possibility. More and more Raman spectrometers in modern days, these days, laser sources are used. That's what it is. Some samples are very sensitive to laser energy, which has to be taken into account because if the sample on which the laser beam impinges, if the sample absorbs that energy, of course, you're able to record the spectrum, you're able to record the Stokes shift or an anti-Stokes shift. But in that process, if the sample also gets heated up to 50, 60 degrees centigrade, its local molecular structure can change. So what you're recording in that case is a Raman spectrum of a sample not at room temperature, but at a slightly elevated temperature. And there can be changes between a spectrum recorded at room temperature and a spectrum recorded at a really high temperature. So one has to be very careful about it. The other point is interference from fluorescence, which can completely mask the Raman signal. This also I mentioned in one of the earlier classes that you may have a very strong fluorescence depending on the structure and the dopants that are present in the lattice, and this can basically change the or completely mask the Raman signal. The laser Raman spectroscopy. The laser Raman spectroscopy these days is because you need to use a very powerful laser. The technique can be also expensive. So this is a schematic of Raman spectrometer. You have a laser source, you have a spectrometer, you have this, all these optics to focus beam onto the sample in order to get good amount of intensity that could be captured by the CCD camera. So by scanning the sample stage in the X, Y, Z directions, one can collect Raman spectra, and it's possible to make 3D Raman imaging. So Raman imaging again is a very important process using Raman spectrometer, where you can get complete three-dimensional mapping of the sample. So gratings are used with varying spectral ranges. You can see here from 3,700 to 1150 centimeter inverse. Today's Raman spectrometers are using extremely high pixel resolution. That's why the Raman mapping process is that much more powerful. This is a good example of how fluorescence almost outshines Raman scattering here. This is a very good example where you see that fluorescence emission is there, and if the detector is picking up this, all your Raman scattering information is completely buried and lost in the classic example of how fluorescence can outshine the Raman scattering intensities, right? So one has to be, if you just record this and say that, look, uh, I don't see any Raman modes in the range from 200 to 2,500 centimeter inverse, it's wrong because everything is completely buried in under uh, the fluorescence, intense fluorescence emission in this particular case. And yeah, again, another schematic to show much clearer way about how a laser beam used a bunch of filters, and then this is your monochromator to select the right. Well, if I can use a white light source and a monochromator to um, select a particular wavelength, and of course, when I'm using a laser, it has a single wavelength. I can use uh, multiple set of lasers also in order to uh, uh, start with one excitation first and then go for second, third, and fourth lambda values. So you need laser sources, filters, gratings, and CD detectors. Yes. One more way of there's also this beautiful principle of confocal Raman, where the laser is focused onto a spot so that you get high amount of reflected intensity of the scattered light that could be captured by the CCD cameras. The confocal Raman spectroscopy basically collects uh, uh, the spectra, the information about the spectra from the focal plane through a pinhole, which avoids stray light, and it hence high to signal to the high signal to noise ratio is maintained. So the components of Raman spectrometer are source of exciting laser lights, excitation sources like argon, krypton, ruby laser, dye laser, ND-arc laser. And then you have filters for filtering in and out the incident laser light. You need gratings, you need gratings, you need a collection of optics, you need photon detectors, of course, your computer and software, a cryostat if you want to do record Raman spectrum or Raman spectra as a function of temperature, which is many useful in many ways. That low temperature Raman gives you more useful information about the modes that cannot be captured at room temperature because of thermal energy interference at room temperature. So the technique has really evolved in a the technique has really evolved uh, in a big way. The technique has really evolved in a very big way. The modern Raman spectrometers use lasers of all types, ultraviolet lasers starting from 244 nanometers, visible lasers, and infrared lasers, all the way from 244 nanometers to 1064 nanometers. That's the reason why the technique is so versatile in dealing with all types of materials. Various laser types I've already mentioned about, the argon laser, India, helium neon, laser diodes, and so on. So typical notch filters can be used. notch filters transmit both Stokes and anti-Stokes Raman signals while blocking the laser line. You need to block the laser line because otherwise you're picking up this very high intense laser light itself. And edge filters transmit either Stokes or anti-Stokes lines specifically. An edge filter also can provide a superior alternative as these filters can offer the narrowest transitions to see Raman signals extremely close to the laser line. Another depiction of how a grating and a CCD combination can be used to capture um, signals from the Raman scattering process. Yeah, these detectors are so powerful today. So these are uh, one-dimensional and two-dimensional detectors. CCD is a silicon-based multi-channel array detector of UV, visible, and near infrared light. CCD detectors are typically one-dimensional or two-dimensional arrays of thousands or billions of individual detectors. That's why over a small area, it's a device that you can see. It can be held in your hand, but it's extremely powerful. Each element interacts with light to build up a charge. The brighter the light, of course, the longer the interaction, or the longer the interaction, the more charge is registered. And at the end of the measurement, the readout electronics pull the charge from the elements, and each individual charge reading is measured. What are the fields of applications? Plenty. Semiconductors, polymers, geology, mineralogy, gemology, carbon compounds, all the research related to carbon materials, carbon electrodes. You need Raman spectroscopy. Life sciences, right? So stress, contamination to analyze superlattice structures, defect investigations, heterostructures, doping effects, polymorphs identification, all that one does with polymers, monomers, isomer analysis, fluid inclusions in minerals, gemstones, the quality of gemstones, inclusions, impurities, phase transitions, finding out the mineral structures is very important. You pick up some minerals or crystals from natural sources, and you quickly want to see what that crystal is made of. So you do a quick, even with, you have handheld Raman spectrometers, you do the Raman spectroscopy, and then compare it with the signature patterns, and then you know whether it's a pure mineral or mineral mixed with some other components or compounds. As I mentioned, any research with carbon, Raman spectroscopy is a completely indispensable technique. Distinguish diamond inclusions with carbon. It's a very quick process that gives you all the information about carbon containing compounds. Because in each case, DLC, nanotubes, diamond, graphene, right? Even though all these are made of carbon, the structures are different. The crystal structures are different. So the bond distances, bond angles are different. The technique to be used is Raman spectroscopy. Life sciences, talk about biocompatibility, DNA analysis to detect drug cell interactions, cholesterol, lipids, cancer, all this process also are heavily reliant on Raman spectroscopy. Now, so if you look at the information that one gets from Raman spectroscopy, typical characterization of Raman frequencies, composition of materials like MOS2, MO3. Now in this two-dimensional form, these materials play a very significant role in the fundamental understanding of 2D materials, and also how they're going to be useful in devices. Charges and changes in frequency of Raman peaks. One can talk about the stress strain states involved, especially with doping in semiconductors. Crystal symmetry and orientation can be uh, uh, evaluated with a high degree of precision. Crystal quality can be measured, and also the well, this is a critical process where intensity measurement, as I mentioned, is always very critical. A lot of optimization has to be done to make sure when you start comparing intensities of uh, different materials. This is a very important view graph where you see that the cross-section absorption, emission, scattering, Raman scattering and Rayleigh scattering. You see the Raman scattering cross-section is 10 to the power of -9 compared to uh, other process, which means, yeah, the scattering cross-section is given by that relation, d sigma by d omega. Yeah, this is a good example I mentioned in one of the classes. If you take diamond, single crystalline diamond, SCD stands for single crystalline diamond, you get a Raman peak at 1333 or 1332 centimeter inverse. That's a signature pattern. We can also make diamond in the form of microcrystalline diamond, nanocrystalline diamond, and DLC, diamond like carbon, where 70-80% is diamond and 20% carbon. You clearly see the diamond peak even in NCD. So that means you have NCD is a agglomeration of diamond particles separated by uh, some carbonaceous phase at the grain boundaries. So even though that carbonaceous carbon phase is present in less than 1%, let's say it's present in 1 to 2% sitting at the grain boundaries, because of the cross-section differences, the Raman cross-section differences between carbon and diamond, you would see a large broad peak from carbon, even though carbon is present in small quantities compared to what you get from the diamond peak. But the fact is, if you're not seeing this peak and if you only see a broad transition, that means there's no diamond there, right? So from this plot, you can say that it is not a single crystalline diamond. The phase consists of both diamond as well as carbon, but you cannot quantify the percentage of carbon present in the nanocrystalline diamond sample. And for microcrystalline, where the grain size is much smaller, you can see the other peaks coming up, but the 32 centimeter inverse is shifted a little bit because of the strain effects. And in a DLC, diamond-like carbon, you see the D and G band peaks. Okay. And well, you can go on giving some very nice examples. And this is with respect to identification of heterostructures of molybdenum selenide and molybdenum sulfide, two-dimensional layered heterostructures. And you can measure the silicon crystallinity. See that the MFO silicon gives a broad Raman spectrum. The crystalline silicon gives a highly a single peak. Of course, from the broadening here, from the intensity, we can assess the quality of the crystals. Of course, one thing that is necessary is also to do X-ray diffraction to make comparisons between what you get in Raman spectroscopy study and crystallography. Topography can be recorded. The three-dimensional Raman imaging today is very powerful, and it's a 3D representation of topography of a scratch in the silicon wafer. So obviously, where the scratch is, you don't pick up the Raman signal, right? And this is an example of identification between natural uh, color and artificial color of stones. You clearly see the artificial coloration giving rise to uh, additional peaks, and you don't see any additional peaks in the naturally colored crystal. Uh, Diamond can be easily identified, as I mentioned already. This and you see diamond. You have a peak from the epoxy resin when these small pieces of diamond are embedded in epoxy resin for the experiment. And otherwise, a single diamond should give you 1332 centimeter inverse peak. And this is a diamond with graphitic inclusions. This is a Raman scattering of different kinds of oils. There's a paraffin oil, Johnson's baby oil, cedarwood oil. All these have signature patterns to identify, um, uh, the quality of these oils. Identification of phase is also possible in a very nice way using Raman spectroscopy. And identification of a phase and the number of layers is done here. Raman spectra of graphene with increasing number of layers, as you can see, from 1 to 19, along with HOPG. So these are the references you can go through. The fundamentals of Raman molecular spectroscopy by Danwell is one of the best books dealing with all spectroscopy techniques, and then Handbook of Raman Spectroscopy and Raman Scattering in Materials by Springer, um, Weber, and Berlin are the authors. So, thank you.